So what I want to present to you today is what are projects, technologies, and their role for Quebec's energy transition, and as well as what we'll be doing here in the lab to develop these technologies and to integrate them with already existing technologies such as biofuel productions from biomass. So as most of you probably know, most of our electricity production comes from renewables, and we're quite lucky here in Quebec because about 90% of this production of electricity comes from renewables, especially from hydropower. And we also have surplus of this renewable electricity, which is about 32 to 40 terawatt hours. So this means that we produce more electricity than we consume them. And this could be a good way of using this surplus of renewable electricity to decarbonize our economy. The problem is with this was using this renewable electricity directly is that we need to store it, and we don't know yet how to store this renewable electricity in long term in an efficient way. So this storage is an issue today. And in parallel, we do have a lot of emphasis today for reducing our greenhouse gas emissions. So Quebec took a quite ambitious target for reducing by 37.5% its emissions below 99 level by 2030. And if you look on the graph on your left, you see that most of these emissions comes from the transport sector, which accounts for about 43% of greenhouse gas emissions here. So this means that to achieve these targets of emissions of greenhouse gas reduction, we do need to reduce the greenhouse emissions from the transport sector. Of course, from other sectors, but especially from the transport sector. And the Quebec government has already put in place few things to achieve that. So today, one of these is blending renewables into the fossil fuels that we use today, especially gasoline and diesel. Our current mandate, for example, is blending 5% of ethanol in gasoline and 2% of biodiesel in diesel. And they just launched the Plan pour une économie verte, which is plan for green economy for 2030. And the objective will be to blend 15% of ethanol in gasoline and 10% of biodiesel in diesel. We have the same context in Canada. So the federal government launched the Clean Fuel Standard, and they introduced the idea of carbon intensity. Carbon intensity is related directly to the greenhouse gas emissions. So a fuel that has high carbon intensity releases a lot of greenhouse gases. A fuel with low carbon intensity releases few greenhouse gases. So the objective will be to reduce the carbon intensity of each fuel per year to 2030 and thereafter. And these will be put in place from 2022 with liquid fuels and 2023 for gaseous and solid fuels. We have the same context in Europe with the Renewable Energy Directive. The mandate is that fuel suppliers must provide 14% of renewables into the fuels that are used for road transportation, for transport in general. And these renewables can be from biofuels, from renewable electricity, from recycled carbon fuels, for example. And in this 14%, there is a share of 3.5%, of advanced biofuels. And what are advanced biofuels? There are fuels that reduced at least 50% of the emissions when compared to diesel and gasoline, and they are produced from biomass. So this shows that we do need to have a lot of different technology and different fuels to achieve all these targets. And I like to put an emphasis on the plural of that. It's not only one fuel or one technology that we'll need to achieve all these targets. We are far from what is set, not only here in Quebec, but almost everywhere. And we do need different solutions for this problem. And one possible solution is the electrophiles, what also called e-fuels. So first of all, what are e-fuels? Are actually low carbon fuels that can be gaseous or liquids, like hydrogen, ammonia, or diesel, or methanol, for example, that are produced using renewable electricity. So it can be carbon-free fuels. For example, if you produce hydrogen, like you see here, from electrolysis of water using renewable electricity, like wind or solar or hydroelectricity, and then you use it directly. Or you can also combine this hydrogen with CO2 that was captured from different sources like biogas or flue gas or any other CO2-rich stream, and then to produce another fuel that, like I said before, can be diesel, methanol, jet fuel, can also be other energy vector like formic acid from aldehyde, for example. And they will have low carbon intensity. The biggest question that I get here every single time that I present this is that, yeah, but once you use this fuel, you release CO2 back again into the atmosphere, which is true, but the same amount of CO2 that is released is used back again into the loop to produce these fuels. So the net emissions of greenhouse gases is quite low. So, So why use e-fuels? There are a lot of advantages. The first one I just said is we can produce a large variety of low carbon energy vectors. And since we are using this renewable electricity to produce a fuel that can be stored and used later when the energy demand is higher, it's also a way of chemically storing this renewable electricity. And this is a very important point, because if you remember that I presented at the beginning, storage of renewable electricity today, at least long-term storage, is a big issue. So being able to chemically store this renewable electricity is quite an important advantage. And since you can store it and use later when the energy demand is higher, it's also a way of stabilizing the energy supply. Another advantage is the diversification of the use of hydrogen. Hydrogen is today one of the most important energy vectors for the energy transition, because, as I said before, it can be used as it is, it can be used to produce other fuels. And this is a way of diversifying this use of hydrogen. It can combine with carbon, with CO2, and then produce carbon-based fuels that will be needed for this energy transition. And since we can, as I explained before, we can also produce, for example, methanol, which is a liquid energy vector that is easy to store, easy to transport, and it's also an easy way to export our renewable electricity. So we already do it, but if you want to export to Europe, for example, using a liquid energy carrier, it's much easier to allow us to export this renewable electricity. So production of electric fuels is a good way of doing it. We also already have all the infrastructure for production and distribution that it's already in place. If you think that you're producing methane, for example, we can just blend it with the natural gas that it's already distributed to the grid. So we don't need to put in place another infrastructure for distributing this fuel. And another advantage, and that's a very important one, is the compatibility of these electrofuels with means of transport that are more difficult to electrify, such as aviation and maritime. Because today, these are two big sectors with high greenhouse gas emissions, and that have no other sources, no other sources than fossil fuels. So producing a fuel that is already compatible with these means of transport, and that they have low carbon intensity, it is a very nice way of reducing the emissions from this sector. So how do we produce these electrofuels? It's using a technology that is called power to X, where the X depends on the energy vector that you want to produce. We can talk about power to gas, power to liquids, power to methanol, power to diesel, power to methane. So it really depends on what you want to produce. And the idea is really going from power, from renewable electricity, to another energy vector. So we can produce two different types of energy vectors. First one is carbon-free, like hydrogen and ammonia, and we can also produce carbon-based energy vectors that we're going to see a bit later. So among the carbon-free energy vectors, as I said before, we have hydrogen and ammonia. As I said before, hydrogen is produced mainly through water electrolysis using renewable electricity. And as I said also before, it is a very important energy vector for the energy transition and can be used as a buffer for renewables. Once you have a surplus of renewable electricity, you can use it to produce hydrogen, store it, and then use it later for the energy production. So it helps to balance the grid. The issue that we have with hydrogen right now is that when you use it, you don't use it necessarily in a gaseous form. You either have to compress or to liquefy it. And it has a lower energy density per unit volume. So this can be an issue today. Another carbon-free energy vector is ammonia. So the idea is to take this hydrogen that was produced from electrolysis and combine it in the Haber-Bosch process that it's been there forever with nitrogen that was separated from air to produce this ammonia. And ammonia has been used for quite a long time as a fertilizer, and it's gained a lot of attention as a hydrogen vector because it does have 3 atoms of hydrogen per molecule of ammonia. And it's also getting a lot of attention to be used directly as a fuel because its energy density per unit of volume is almost the double of that of hydrogen. But it does have some issues. One of them is the high cost for nitrogen separation from air, which is not that a big of an issue because it's already been done today. Another issue that we need to consider are the emissions, because as a carbon-free energy vector, it doesn't release CO2, but it does release NOx, which is also a greenhouse gas. Another issue that we need to consider is what we call tank-to-wheel. It's how it's going to burn. Actually, ammonia doesn't burn that well, so we basically need to mix with other fuels like hydrogen so it can burn properly. So we also have to think as the fuel how it's going to be used, not as how the possibilities of using how it's going to produce. To have the big picture, to see the big picture, how it's going to be produced, how it's going to be used, how it's going to be stored, and etc. So another type of energy vector is a carbon-based. So we can produce methane, diesel, fuel, formaldehyde, formic acid, methanol. There are 2 ways of doing it. The first one is through CO2 hydrogenation, which is the one that you're seeing here in the slide. So it's basically divided in 2 steps. The first one is hydrogen production through electrolysis. So see why hydrogen is an important energy vector, because it always starts with hydrogen production through water electrolysis. So this is the first step. And the second step is to combine hydrogen with a CO2 that was captured and purified from other streams that can be, as I said before, biogas, flue gas, or any other CO2 waste stream that it's available near where the power-to-X plant is going to be implemented. So we combine these 2 gases, and then we produce the energy vector that we want to produce, as again, methane, methanol, alkanes in general, depending on the need of the partner. So this is the most advanced pathway that it's in place today. So most of the time when you're hearing about power-to-X technologies, this is the pathway that people are developing. There is also another pathway that's also gaining a lot of attention, is the CO2 electrochemical conversion or reduction of CO2, which is very similar to the previous one. The difference is that it's mainly done in one step. So instead of having a step for hydrogen production, you will combine directly water and renewable electricity with CO2 in electrochemical conversion, like in electrolysis, and then produce the fuel that you want to produce. So this has the advantage of eliminating the hydrogen production step. So it will definitely decrease costs of CapEx and OpEx, especially because CapEx of electrolyzers are quite high and have an influence on the price of the fuel that you're producing. So bypassing this hydrogen production is quite interesting. However, this pathway has still some issues because it suffers from low CO2 conversions and from low selectivity to the desired fuel that they want to produce. So, as I just presented, Power-to-X has gained a lot of attention everywhere, especially in Europe, in Germany, and in Nordic countries, because of all the advantages that I just presented you. And there's a lot of companies that are investing seriously in this type of technologies, like Audi, Carbon Recycling International, Dow. So I want to present you now just a couple of examples of some of these companies and what they're doing and what they are in development of these technologies. So the first one is Carbon Recycling International. Mary will present you later, but they will be presenting here with us next week, if I'm not mistaken, about their technology. So I won't be going into too much detail. I'll let them show you the details of the technology, but in a general way, what they do is that they have a technology that is called emissions to liquids, and they take CO2 from different sources, as you can see here, from gasifier, gas reforming, industrial process. They capture, they purify it, and then they combine it with hydrogen that is either produced from water electrolysis with renewable electricity, or that it's captured from other hydrogen waste streams. And then they combine them together to produce a wide range of products, but they're mainly focused on methanol. And they're today the biggest company producing e-methanol in the world. So, as I said before, they're combining CO2 rich streams with hydrogen produced through a lot of water electrolysis. And their commercial scale and their production capacity is about 50 to 100,000 tons of e-methanol per year. Another company that's investing quite a lot on Power-to-X technologies is Audi, the car company. They are investing in production of e-methane, e-diesel, and e-gasoline. So the most advanced one is the e-gas project for the production of methane. So the idea is, again, take renewable electricity that comes either from wind or solar power, combine it with, produce hydrogen through that, and combine it with CO2 to produce methane that is either distributed through the grid or used in filling stations. They say that e-fuels, their e-fuels in general, reduce up to 80% of CO2 emissions. So this is a quite good number to present because it does prove that these type of fuels have a high capacity of reducing greenhouse gas emissions. So the feedstock that they're using is CO2 from a waste biogas plant. So we're already talking about biogenic CO2. Again, hydrogen through water electrolysis and electricity through wind and solar power plants. They produce up to 1,000 tons of e-methanol per year. And a clever thing that they do is that the plant is started professionally when they have surplus, when they have a higher production of electricity than what the local grid can absorb. So they produce these e-fuels, and then they use later when the demand is higher, which is basically the idea of the advantages that I was presenting before of chemically storing these renewable electricities. So the second one that they're doing is the e-diesel. But instead of using wind and solar power, they're using hydropower for producing hydrogen. And then again, the same process, combination of CO2 with hydrogen to produce diesel and also other chemicals as byproducts. It's a pilot plant that is going to be built in Switzerland and will have the capacity of 100,000 liters of e-diesel per year. They also have projects for production of e-gasoline, but they're still at lab scale. So this present to you, just give you also an overview that only one company, a big car company, is investing not only in one project of Power-to-X, it's investing in 3 different projects of Power-to-X for 3 main fuels that we use today. Another example, and which is a very nice example, is what Dow has been planning to do. And it's quite smart, actually, because one of the issues that we have today with this type of technologies that I presented before is the costs for hydrogen production, the capex of the electrolyzer. But Dow was already had electrolyzers for like using salt water. So they did electrolysis of salt water in a chloride plant, and hydrogen was actually a byproduct of their process. So instead of having to invest in all this part for creating hydrogen, they already had it on site. And they also have the possibility of storing this hydrogen in salt domes. So they produce the chlor in their plants. Hydrogen is a byproduct. They store in salt domes, and then they can use it later for combining it with CO2 and produce green methanol, which is what they want to produce. And this will help, without a doubt, to decrease the costs of the methanol that is going to be produced. And their estimated production capacity would be of 200,000 tons of e-methanol per year, which is almost a double of Carbon Recycling International is doing today. So if they really manage to put that in place, I think there's going to be quite a big project, and that we need to follow closely, especially considering that the reduction of the costs that they will be able to implement. Another interesting project that is in place, it's a partnership between Sunfire and Total, and it's still an R&D project, but the difference of what they're doing is that they are using megawatt scale high temperature electrolyzer, which has an efficiency that is quite high. It's higher than 80%. And again, it's one of the challenge that we have today is the efficiency of the electrolyzer. They're combining this hydrogen with CO2 that comes from Total refinery plant using renewable electricity, which type of electricity is not available as information, and the target product is methanol. Another example is NEURO and Gasmi. What they're doing, that they're implementing a 20 megawatt electrolyzer that's going to be the first of its kind to be implemented in Europe at this scale. And this project is interesting because we have, as you can see here, 5 different partners that are working together to develop this. And each of them has a different expertise. NEURO and Gasmi are the ones coordinating everything. McPhy is going to provide the electrolyzer. MCN, that I forgot to put the logo, sorry. They're the ones that are going to actually do the hydrogenation of CO2 to produce methanol. The NEURO is going to produce electrodes. Inicio is a sustainable energy consultant. So this proves that implementing these technologies will need a lot of partners, or a lot of different partners, because this will allow to split the risks between them and then to actually develop these technologies at larger scale. Another example is a partnership between Enbridge and Hydrogenics that is done here in Canada, in Ontario. It's the Markham Energy Storage Facility for power to gas production, and in this case, it's hydrogen production. So they have a capacity of 2 megawatts. They produce, again, water through water electrolysis, and they store it and then convert back into electricity when it's needed. They also have the option of blended that with natural gas and natural gas grid, but due to issues with grids in general, the maximum that can be blended is 2%. Another example is done here in Quebec. It's a partnership between Greenfield Global and Hydrogen. It's a joint venture between them, and their goal is to produce hydrogen, biomethane, and biomethanol. The idea, it's a bit similar to the one of Sunfire and Total. The idea is to take CO2 from Greenfield's global biorefinery, combine it with hydrogen from water electrolysis that is done using hydroelectricity, and the plant will have an initial capacity of 29 megawatts and a possibility of scaling it up in 2025 up to 80 megawatts. So, as it's presented, there's a lot of interest towards these technologies, but there's also still a couple of challenges that we need to overcome to implement them at larger scale. And the 2 main costs, and really the biggest ones, are the electricity prices. That is not a big issue here in Quebec because we have an electricity price that is quite low. It's almost half of the one in France, for example. And the second one as I said before, is the capex of the electrolysis for hydrogen production. So just for give you an overview, when you're producing e-methanol, 80% of the capex for production of this e-methanol comes from the capex of the electrolyzer. So it has really a big impact on the production of these fuels. So just to give you an overview, an idea of how this really impacts the price of these fuels. Here's the graph from very interesting people that are working in Sweden, comparing and calculating the production costs of these different e-fuels. You can find the reference of their paper here. And they build scenarios to evaluate how much would cost the production of different types of e-fuels. And they took into consideration all the aspects that you can see here that goes from the electrolyzer, the capex of electrolyzer, the price of electricity, and CO2 capture, and all the other aspects. And what they saw is that the price between the different fuels, the costs for production between the different fuels doesn't change that much. And the reason for that is that the two main costs that are really impacting the price of these fuels are the price of electricity and the cost of capex for the electrolyzer. So, and these two costs are common for all the fuels. So by the end of the day, the cost for production doesn't change that much because of that. Another challenge is the efficiency from electrolysis, which is today about 70%. When you think about it, okay, it's not that bad, but it's something that's really under discussion right now, how we can increase, because we lose part of the electricity when you're producing hydrogen. Another one is scaling up costs, and this is also a very important one, because economy of scale doesn't help that much these technologies, because to increase the hydrogen production, one of the things you need to do is also to increase the surface of your electrodes. So economy of scale won't help that much as here in this case. Another challenge that we have is the availability in the electricity prices during the year and of the electricity supply during the hydrogen production. And this is not a big issue here in Quebec, because as we said before, we have surplus of renewable electricity. We have low prices of renewable electricity, so we have hydroelectricity, which is quite stable form of electricity. So this is not a big of an issue here in Quebec. And another issue is the integration. It's two types of integration. The first one is the different steps of the Power-to-X technology we need to implement to integrate CO2 capture with hydrogen production, with fuel production, with storage, and utilization of these fuels. And we also need to integrate these technologies with already existing process, because most of these technologies will need a CO2 source, right? And this CO2 has to come from somewhere. So you basically will combine your Power-to-X plant with another plant that's already existing, and this integration needs to be further developed. So as I presented to you, there are quite a number of challenges to develop this technology that don't apply here in Quebec, because we have a very favorable context. As I said before, we have a low electricity price. We have surplus of renewable electricity that it's between 30 to 40 terawatt hours. We have a lot of efforts for reducing greenhouse gas emissions. We have carbon market in place. Quebec government just released the plan for green economy 2030. So there is a lot of interest and effort to reduce these emissions. And we also have the possibility, as I said before, to export a renewable electricity through these e-fuels. So if you're using low electricity price or surplus of renewable electricity and producing these fuels and then shipping it to Europe, for example, that it's a very favorable market right now, because they're looking for countries with low price of electricity to develop this technology and to produce low carbon fuels. So this is a good opportunity for us as well. So what does it takes to implement this here in Quebec? So the first thing is that we need to bear in mind that we're gonna need different technologies and different fuels, and again, emphasis on the plural, to decarbonize our economy. we won't need only hydrogen, we won't need only biofuels, we won't need only ammonia. We'll need a lot of different technologies and a lot of different fuels to be able to reach our targets. We also need to have a, well, two-year perspective, I mean, a global perspective. As I said before, we need to go to think about all the steps of the production and use of these fuels, from CO2 capture, from hydrogen production, from integration of these technologies, from the use of the fuel to see how it's going to burn, what it's going to take to ship it, to use it. So we need to have the full picture before choosing which fuel to use. We need also to have still R&D to improve these technologies, from hydrogen production efficiencies to CO2 conversion, selectivity to the energy vectors that we targeted. We also need long-term regulations that it's going to be there for more than just a couple of years, and that will definitely give confidence to people, to industries to invest in these technologies. We need to validate them at pilot and demonstration scale, especially when you're talking about integration of the different steps of the technology. And very importantly, we need also to integrate these technologies with existing processes. As I said before, Power-to-X technology won't probably work alone. It needs to have a CO2 sources. It needs to have renewable electricity. So we need to integrate them with other technologies to put these technologies in place. So I'll just quickly present you a bit what we've been doing here in the lab to develop these technologies and to integrate these technologies with other processes. So here at the Biomass Technology Lab, we're 4 groups, all of them working on energy transition, on carbon-based fuels and commodities. So we have just moved to a building that is completely dedicated to energy transition. We developed with our industrial partners new technologies from lab scale to pilot scale to decrease the risks of implementation of these technologies. We have, as you can see here in the left, analysis laboratory that help us to quantify all the gases, solids, and liquids that are coming out of our process. And we also have, just across the street, the UDS solar power plant that is quite recent, and we also have the opportunity of doing partnerships with them. So what's our vision? So regarding the production part, we're mainly focused into 2 technologies. The first one, into 2 processes more. First one is the methane electrocatalytic conversion. So the idea is to take methane and CO2 that comes from different sources. That can be biogas, natural gas, tail gas, combine this with renewable electricity and one single step to produce syngas. This syngas can either be used directly or be used as a building block for the production of 3 other energy vectors that we are targeting right now, which are methane, methanol, and alkanes in general. Here I'm talking about diesel, gasoline, and jet fuel. That we're also looking into is to convert directly flue gas, take it from a chimney, for example, and combine it with renewable electricity to also producing gas, and then these are the 3 vectors here. We are also looking into the integration of these technologies. And so here we can imagine, for example, the production of transport fuels in a biorefinery, so using forest and agricultural residues, for example, to produce these fuels, and then taking the CO2 that comes out of this biorefinery, combine it with green electricity and water, and produce fuels for other transport means that don't have too much options today, like maritime and aviation, as I presented before. So this is a way of integrating 2 technologies, and it's also a way of showing that we do need different types of fuels, because here we have biofuels and electrofuels, production of them that is integrated. And one of the questions that people ask is, yeah, what was better to produce? What should we focus? Is it biofuels? Is it e-fuels? Well, it's both, and it's probably more than that. We need other energy vectors as well. And this is a nice way of doing it, and also of showing that we can provide solutions for different means of transportation when we integrate different types of technologies. So just to conclude, as I said before, we will need a lot of different technologies and a lot of different fuels to reach energy transition. Power-to-X technologies are one way of doing it, a good way of doing it. It will allow us to diversify the hydrogen uses. It will allow us to reduce carbon footprint of sectors that don't have much other options than fossil fuels. Quebec's context is very favorable for that. We have surplus of renewable electricity, we have carbon market, we have the new plan for green economy that the government just launched. So there are a lot of efforts for this. We have a lot of good things that are already in place that are favorable for developing these technologies, but you still need long-term regulations that will give confidence to people to invest in these technologies. We need to have a global perspective that from production of fuel and to its use, see how it's going to burn. We will need as well a collaboration between different stakeholders. So we need collaborations from academy, from industry, and from government institutions to put in place. And that's what we've been doing here at the BTL. We have a long history of collaboration with the industry. We will have developed a good expertise in carbon upgrading in general. And we're also interested in going a bit further and seeing and investing on how to integrate these green technologies. So this is a photo of our groups before COVID. And I'll take you any questions that you might have now. Thank you.
Thank you, Bruna. So if you do have any questions for Bruna, please raise your hand. We have time for a couple of those. I personally have one, maybe to set the table. Bruna, we often have, like, we meet people from all around the province, and they always see us as suppliers because they're always asking us, okay, is it economical, and can you provide things right away for us to work to transform this carbon dioxide into gold? So you mentioned in your presentation that, of course, that there are still challenges that need to be addressed, but your personal opinion. So people here are sometimes like a little cold on installing those, or putting together those new technology, or even investing in those new technology. Why does company like Audi and big company like this go forward with this? What do they see that we don't see or other people don't see? Why do they do it, do you think?
I think that's a bit of a million-dollar question. But I think that these technologies have also gain more emphasis in European context. People there have, they don't have that much of possibilities that we have here. So they really invest into looking into different opportunities, into different things, and they see that this is a way of having producing different types of fuels and not only one fuel. So these different fuels can be used in different sectors, so they can achieve higher decarbonization, being faster with these type of technologies. And they're doing it with electricity price that is much higher than what we have here. So I think first thing is for us to understand that these technologies exist, that there's a lot of people that don't know them yet. So first we need to see, okay, they exist, and to understand their potential, and to have maybe also influence of maybe the government to help, because necessarily invest into a technology that it doesn't belong to their practice. For example, if you're talking about a cement plant, of course they need to convert their CO2, but converting CO2 and producing something else, it's not what they do. They produce cement, and they want still to produce cement. So investing a lot of money to develop a technology that's not related to their core business, maybe it's a bit complicated. So of course we need partnerships to decrease the risks for everybody, and then give confidence to everybody to invest in this type of technologies. I don't know if it answers your question, but
yeah. Is there any other question from the audience? Nicola, go ahead.
Yes, Bruna, it was really an excellent presentation. Thanks for shedding a lot of light in this area. My question is simple and complicated at the same time. We know that producing hydrogen from electrolysis is something which is not really needing any scale up because it's a known technology. But all other steps to take this hydrogen and convert it to energy or materials vector need the two steps. The first step is to prove at lab scale that this is feasible. And then the next step, which is the most difficult and which is attracting more the investors and the people who are interested in this area, which is what we call the Death Valley, and it's the scale up. So where you are at this level, at the different topics you have presented, and if there are any plans to attract people from outside and fund essentially this scaling up.
There is actually, NRC, they just launched a big challenge that it's called Materials for a Clean Fuel Challenge. I don't know if you heard about it. And the idea is really to take different types of technologies that it's actually focused on Paratrix technology, on fuels from CO2 and from renewables, so Paratrix technologies. And they're investing in technologies with very low TRLs, and they will invest in them for 7 years. So the idea is really to take technologies from very low TRL that is still lab scale, that is still in proof of concept step, and then to have them to scale up. We are part of these Materials for a Clean Fuel Challenge. We were selected for it. It's not financed for 7 years in a row. They finance for 2 years, and then they see depending on the evolution of the process for the other 7 years. But we are funded for that part, and we are developing a technology that is able of converting flue gas directly into syngas. So it would bypass hydrogen production step, for example, which would decrease a lot capex and opex of the operation. So that's where we are right now in the development of these technologies.
Yeah, this is a very, very important first step, and I think this is where you will have to start for the next step. And I believe that it takes a lot of work, but it's feasible. It's a very nice project, and probably in the future we will need to cooperate in some of these projects.
For sure.
And do all the steps, and this is coming up very, very fast, in fact.
For sure.
Thank you very much. Thank you.
You.
Have a good continuation.
Thank you.
Thank you. Question from Matteo. So Matteo, floor is yours.
Hello, thank you. Good morning, everyone. So it's Matteo from Quebec Center for Advanced Materials. Now, it's an aspect we often don't talk about, I think, when we talk about Paratrix, and that's the widespread adoption of these technologies will increase pressure on the catalyst supply. So I think the demand will skyrocket. So how do you take into account that when you analyze the feasibility of the different technologies?
Well, catalyst development is one of the things that people are looking into right now, especially for the second pathway of conversion, not direct hydrogen, but CO2 electrochemical, because if you want to get it commercial, it needs to have lower cost as possible. And one way of improving your process, of course, is to increase your CO2 converters, is to increase your selectivity to your project, to your product. Doesn't matter which one is it, and it often comes from catalyst, from the performance of your catalyst. If it's able to convert CO2, if it's able to produce selectively your product, and if it's stable enough, how much it's going to cost. So catalyst development, it is something that's really being investigated right now for that. So yeah, for sure, it's one step that needs to be validated for these technologies.
Thank you.
Good, thank you. So any other question from the audience? So maybe one last one from myself, Bruna. So do you think, how much do you think the clean fuel standard will influence the PTX technology to be implemented in Canada?
Well, hopefully a lot. Not on clean fuel standard, but all the other efforts. Quebec just again launched the plan for green economy, so there is a lot of pressure for that, and people will need to decrease the intensity of their fuels, and they will have to find a way of decreasing it. And today we don't have that much options, especially here in Quebec. There are three main things that could be done. It's biofuels for sure, because of forests, hydrogen, and electrophiles would be a good way of doing, because biofuels and hydrogen, they're important, we'll need them, but they cannot supply to everything. So we'll need as well electrophiles. So I think for sure they'll put a pressure on people to look into other possibilities. And I think electrophiles is going to be one of them because of the versatility of the technology.
Okay, so you mentioned the Quebec new policy or funding. There's like something like $7 billion available for green technology. Most of it is related to electricity and changing the fleet of vehicles from gas to electricity. Nevertheless, how do they define the electrofuels in there? Because as an example, you have limited funding, which would be really cool in academia. But if you have limited funding and you start producing, I don't know, alkanes or gasoline from CO2, at this point, I don't think you can classify it somewhere in the policy that the government has put together. It doesn't really classify as biofuel. Do you think we should have a different category in Quebec? Because in Canada, with the clean fuel standard, it's low carbon intensity, so it's pretty clear. It's independent of the type of feedstock. But do you think it might be worth it to have something defined for the electrofuels?
I think it does, because it is definitely something that we're going to need. And at some point, if we are going to invest in it, people will need to see, okay, what is the impact? What is the they're having in return? Okay, this will I be able to classify it as a CO2 emissions reduction, or they need to know where it's going to fit to be able to invest it. So of course we'll need something more concrete on that, and we also need something that will make sense between federal and provincial government, because today it doesn't fit very well. So we'll need something that comes together nicely, so people will understand, okay, if I do this, this is what I'm going to get. So we need, of course, more coordination between the two parties, maybe.
Great. So one last call if you have any question from the audience. So if not, I will see you next week. I would like to thank, of course, Bruna for the presentation today. Very interesting, and maybe we'll see this coming up industrially in the future, hopefully. And next week we'll keep on the theme of Power2X with the guys from Carbon Recycling International. And I'm working on a surprise for the last week before the vacation or the holidays. So there might be another guest that will be joining us. So see you guys next week. Again, thank you, Bruna. Thank you to the audience for being here today, and see you very soon. Thank you.
Merci.
Bye.